All right, so most people pretty much nailed the homework, which was good. The basic question was playing with switches, right? Getting some more familiarity with what switches do. And the main thing to remember is when you want to hook a switch up, we have these normally open switches we're imagining, but they're like our slider switches, right? So when you want to draw a switch, this is sort of the standard symbol for doing it if it's normally open. And if we want to feed a voltage level into a circuit over here, right, our one and only correct way to do this is to use a 1 kilo ohm resistor, tie that resistor to 5 volts, and then tie the switch to ground so that if we close the switch, this point here is connected to ground. This is a logic 0. If we open the switch, this is not pulled down to ground, but it is pulled up to 5 volts through a resistor. So if the switch is open, let's call this out. If the switch is open, out is a logic 1. If the switch is closed, out is a logic 0. And for a normally open switch, this would be pushed. Would mean that it's closed, and when you don't push it, then it's open. That's why it's called normally open. And let me see what the original wording was on all this. There we go. So draw a circuit with 3 push buttons. Okay, proceed as follows. Push buttons are normally open. Sketch a circuit with a normally open switch, resistor, and power connections as needed in the correct way we described in class. So that's right what that is. And then draw a system diagram for your circuit. So the goal of the overall circuit was output should, LED should be lit up when exactly 2 buttons are pressed. Okay, and the LED should be off otherwise. So a system diagram might look like this. Here's our 3 buttons, A, B, C. And here's our output X. And I would put a note here, A, B, C equal 1 if not pressed, 0 if pressed. And for X, you could say X equals 1 if exactly 2 buttons pressed. The important thing here is there's 3 inputs and there's 1 output. And I'm calling my inputs A, B, C, and my output X. You could call them whatever you want. But I'm going to write a truth table that uses those same variables. So I can say, for example, here's A, B, C, and here's X. And we list all the possible combinations. And then we fill in values. So our system diagram says these inputs are 0 if they're pressed. The output should be 1 if exactly 2 buttons are pressed, which means exactly 2 of our inputs are 0. So if you don't jump to conclusions, you'll find that your 1 outputs are right here, here, and here. And then they've got to be 0 everywhere else. But since we usually think of pressing something as turning it on, if we sort of skip over this, we might think that we're actually wanting a 1 when we have 2 inputs that are equal to 1, right? So sometimes people put down a 1 here, here, and here. which is complementing the behavior of the inputs. So the system diagram was there to sort of help you keep track of what pressed and not pressed mean. So we got a truth table, write output equations based on your truth table, and then draw a circuit that implements those equations. So based on the truth table, we could do a sum of products and say something like x equals a bar b bar c, or a bar b c bar, or a b bar c bar. In invisible ink. There we go. So we can write an equation like this, and it's just a sum of three min terms. And this equation, if you stare at this long enough, it can start to look almost like what the original question was asking, because this term is going to be true if exactly two of these terms are false. Here A and B are false, here A and C are false, here B and C are false. Right? Because when the button is pressed, B bar should be a 1, C bar should be a 1. So there's an equation. Now, if you're fancy and you like exclusive OR gates, you could rework this as an exclusive OR circuit. But if you go directly from here to a circuit that has XORs instead of ANDs and ORs and inverters, right, you're missing some details. So draw a circuit that implements those equations. So so ideally, you know, you do a K-map or something to simplify it or change it into something, or you make some observation and come up with an equation. But then you implement the circuit using those equations. And this was supposed to be a full circuit, so it's got to have component ID numbers and pin numbers and all of the necessary parts and pieces, the switches, the LEDs, and so on for part F. And most people did that fine. Anything else I found on here? So, so probably the most common error, and we mentioned this last week also. So you're feeding into some part of your circuit your three signals from your switches, and if you do this, you don't get exactly what you want. Right? And the problem with doing this is you've shorted your inputs together. So you really want a separate resistor pulling up each input, and then switches that can pull each input down to ground. Make sure you use logic symbols. If you mean an AND gate, draw an AND gate symbol, and then label that U1, and then up here, U1, describe what that is. I saw a few people who did this. And yeah, you can look at U1, you can come up here, you can look at this, you can dig up the data sheet and figure out that that's an AND gate. But if you have an AND gate, draw an AND gate symbol. If you have an inverter, draw an inverter symbol. Okay, because this is quick for somebody to read who understands digital logic. This requires a lot of work to know what your circuit does. The point of having the component ID block with the component numbers like U1, U2 is so you can actually wire the circuit together. Okay, but to understand logically what it's doing, all you need is the logic gates, and that's the part of the diagram that somebody would look at to figure out what's the behavior of this circuit. And then if they're actually putting wires into a protoboard, they'd use the U numbers and the pin numbers and so on. Does that make sense? Okay. So if you have questions on that homework, go ahead and ask now or later. Otherwise, questions on homework 5, which is due Thursday. Questions? I had lots of questions this morning.
Can you kind of, for like 3U,
Yeah.
redrawing the circuit using only NOR?
Yeah, this is tricky. So there's a few ways to go about this. And the goal here is just to get some practice with this idea of replacing one type of gate with one of these universal gates, a NOR or an AND. There's a few ways to do this. So one is to do this algebraically. So let's just look at the top part of this circuit. So we've got A and B going into an OR gate. And we don't have OR gates, we have a NOR gate. So we'd like to rewrite this as something with a NOR. And going from a NOR to an OR is pretty straightforward. Right? So an OR gate we got a little bubble on the output here for a NOR, right? That bubble we can just think of as being an inverter. And if we want to turn this into an OR, we just have to throw another inverter on the output.
Didn't say we could use inverters though, did we?
No, you can't use inverters. But if we could, here's what we'd basically be doing. We'd be saying, let's take A and B, let's put them through our NOR gate, and then let's invert the result of that. So now we've got a subtask, which is suppose we want to make an inverter. And I gave you a hint last week how to make an inverter out of a NOR gate. Anybody remember the trick? Yeah, if you tie the inputs together, and you look at the truth table, this is going to turn out to be X bar. So what's a NOR? It's just the opposite of an OR. So it's a 1 if both inputs are 0, and it's a 0 in every other case. Well, if we tie our inputs together, all we care about is the case where A and B are both 0, or A and B are both 1. And so if X is 0, A and B will be 0, the output of the NOR will be 1. If X is 1, A and B will be 1, the output of the NOR will be 0. So this functions like an inverter, which means if we take a NOR gate and we put this thing on the output, we've turned our NOR into an OR. Is there any other way to get an inverter out of a NOR gate? I mean, you could sell it and then buy an inverter, but probably buy 2 inverters for the price of an OR. What does this circuit do? So if B is always a 0, right, if X is a 0, B is 0, my output is a 1. And if X is 1 and B is still tied to 0, my output is a 0. So this is another way to get X bar.
What if you could have connected voltage to it?
Sorry?
What if you had connected the voltage to it to make it a logic 1?
So what if you connected a logic 1 to this? That's a cool question. So if X is a 0 and input B is a 1, the output of our NOR gate is going to be 0. If X is a 1 and our B input is 1, the output of our NOR gate is still going to be a 0. So this is always going to be logic 0. We're going to come back to this after break, and it's going to be a key to making life good.
You actually do it with the C and D inputs.
So what about C and D? So you're clear how to make an inverter out of a NOR gate, right? And we know how to make an OR gate. It's just a NOR gate with another inverter. So C and D are different because they're going into an AND gate. And there's this funny bubble in the beginning and a bubble on the end. And let's just try to implement this weird logic gate using NORs. And once we've got that, we can do our first one, and we'll know how to do that output and AND gate when we're done. So this bubble in the front is really just an inverter. Well, we know how to make an inverter. So we take the logic that we were just doing and we use that to take D and turn it into D inverse. And we can think of this as an AND gate with another inverter on the end. Well, there's another inverter we can make. So really, all we got to do is figure out how to make an AND gate out of NORs. If we can do that, we can just plunk that in here, inverter, inverter, and there's our second piece of our circuit. Well, here we got to do a bit of math, which is De Morgan's theorem. So De Morgan's theorem says if you have A, B, and you complement it, it's the same as complementing the two inputs and ORing them. Which means if you want A and B, right, I can complement the left side and AB bar becomes AB. I can complement the right side and this becomes this with a bar on top. Well, this is a NOR gate, right? It's the negation of stuff being ORed together. So if I take A and I invert it, and I take B and I invert it, and I put those into a NOR gate, this is telling me the result is A ANDed with B. And I know how to make inverters, and I've already got a NOR gate, so I can just put those together. There's my AND. So it's lots of pieces, work them out one at a time, put them together to make the bigger pieces, put those together, and so on. Big sheet of paper. Well, 8.5 by 11, but you know, use a whole sheet of paper. And then our last one is just another NAND gate, and a NAND gate is just this thing, right? So this is equivalent to that. Looks funny. I guess that's right. Yeah, that's an AND. Any questions with question 2, the analysis? Minimize logic function? So you can write an expression for f just by working it through. F is going to be an AND of 3 things. The first thing is A0 ANDed with A1. The third thing is going to be A1 XORed A3. The second thing is going to be an OR of 3 things, which is A0 A1, A2 A3, and A1 A3 XORed. And you OR those together and you AND that with these other things. You get this big long expression, right? So you can try to simplify that expression algebraically, multiply things out, use your identities. If you have like something ANDed with something bar, that's a 0. If you have something ORed with something bar, that's a 1, and so on. And I don't know how close that gets you to a minimized function, but it's a good thing to mess around with. The direct way to do this, though, would be to write a truth table. And anytime you have a circuit and you're trying to write a truth table, my recommendation is put down labels at intermediate points on your circuit. Don't try to just write a table with your inputs and then list the value of f, because there's so many chances to make mistakes. Right? You got 16 values of f to fill in, and for each of those you have to calculate 3 values on the left, and you have to OR 3 of those together to get the medium value, and then you have to AND all of that. So do it methodically. Make yourself a truth table. And let me copy the circuit down here, or at least part of it. So here's what the beginning of our circuit looks like, and there's lots more stuff over here and over here. Make yourself some intermediate values, like F1 is the output of that AND gate. Oh, I can use my fancy stamp. Okay, I brought my stamp with me. There we go. All right, so make yourself an intermediate column for, say, F1. And to calculate F1, all I got to do is take those first 2 inputs, A0, A1, and them together. Right? So I'm just going to look at these 2 columns, and I'm going to do an AND operation. So what's my AND? It's always 0 unless both of my inputs are 1. All right, we've also got inputs A1 and A3 going into an XOR gate. So I'm going to call that part of my circuit F2. And to find F2, I'm just going to look at A1 and A3. And I'm going to do an exclusive OR on them. So if exactly one of those 2 is a 1, my XOR is going to be a 1. There you go. So here I'm just looking at A1 and A3, and anytime that 2 of them, exactly one is 1 and one is 0, my output's going to be a 1. If both inputs are 0 or both inputs are 1, the output's going to be a 0. And so to fill in the values for these intermediate points, I never have to do anything very complex. I'm doing simple operations of 2 things. But you can piece those together, right? Once I've got intermediate values right here and here and here, right? Now to find the output of this is just an OR of 3 things. I look at F1, F2, and F3, and if any of them are 1, this point F4 becomes a 1. So now I've got columns for F4, F1, and F2, and anytime all 3 of those are 1, my final value F is a 1. So 2 advantages of that. 1, it doesn't take a whole lot of keeping things in your head, right? And 2, if you do this on a test or a homework, it's easy to see if you got the wrong value for F, why you got the wrong value. Is it because you don't understand anything about the circuit, or is it because you know, did an XOR wrong in one case out of 16? So it's good for partial credit. So once you have your final value for F, right, go ahead and make a K-map, fill in the ones, cover them, write down the minimized equation, there's your final answer. And I think it would be cool to do that and also try to take the original expression for F and simplify it, see if you can make them the same. Because someday that'll be useful. All right, I'm going to talk about question 7, even though no one's asking about it, because question 7 is confusing. Again, you're trying to find compact min-term form. One approach to this is write a truth table. So you have a circuit with 3 inputs, A, B, C, and let's just look at F2. Let's just think about one output, right? So 3 inputs, 1 output, F2. You have to know what the demux does, okay? And I said in class last time what the demux does is it makes one of its outputs high based on the values of A, B, C. So if A, B, C are all 0, right, which represents the number 0, then that output labeled 0 is a 1, everything else is a 0. Once you know what those 8 outputs are, you can trace down and say, what are the 8 inputs to this part of my circuit? If I have a 0 coming out of this line, that's going to get inverted and become a 1. If I have a 1 coming out of this line, that's going to get inverted and become a 0. So figure out what the 3 values are going into your OR gate, do the OR operation that tells you the value of F2. Now change your input to be 0, 0, 1 and repeat the exercise. And 0, 1, 0, 0, 1, 1, go through all 8 cases and figure out the 8 values for F2. Now you got a whole truth table for F2. You can do the same thing for F1 and F0. And it's not a feel-good result. It's going to seem weird, but just analyze the circuit faithfully and fill in the truth table, and then write equations for F0, 1, and 2 in compact min-term form. And ignore the solved part until you're done with 7U. Then go back and look at the solved part, because the solved part is more satisfying. But the solved part really doesn't help you with the unsolved one. In fact, it'll almost guarantee you get the wrong answer. All right, multiplexer circuit 8, same thing. It's a circuit with 4 inputs, 1 output. Your inputs are A0, A1, A, and B, and your output is F. Just make a truth table. List all 16 possible values for A0, A1, A, and B. And you have a truth table for what the multiplexer does. So once you've fixed values for A0, A1, A, and B, for example, suppose they're all 0. Okay, this is a 0, 0, 0, 0. What does our multiplexer do? Well, if the 2 inputs are 0, 0, the output function F should be equal to D0. D0, we just said, was a 0, so F is going to be a 0. So there's the first row of your output truth table. And do that for all 16 cases, and then write compact min-term representation of F. Yeah?
So A0 and A1, they don't look like they're actually connected to ground or...
No, they're connected to D0 and D1. So the connection rule, if you have wires crossing without a dot, they're not connected. If you have wires meeting in a T, they are connected. And if you have a dot in the middle, they are connected. So these are just crossing over but not connected to each other. So A0 goes to D0, A1 goes to D1, D2 goes to ground, and D3 goes to logic 1. Make sense? Well, it doesn't necessarily make sense. Is it doable?
So it's kind of more like a 3 input, so F is only really looking at 3 inputs at input, right?
No, it's looking at A0, A1, big A, and big B.
Yeah, well, I guess what I'm saying is it looks at A and B, and depending on that, it also looks at either A0, A1, or I guess it looks at D0, D1, D2, or D3, right?
Right, right.
So,
Which may or may not depend on the value of A0 or A1.
well, I guess I'm thinking like if you get like a 0, 0, it looks at A1, it doesn't really care, or it looks at A0, it doesn't care what A1 is.
Right, right. And then we got PLA questions. All right, good to go. Any lingering issues from the lab that you turned in today? Mostly made sense? All right. So let's talk about Lab 4. And Lab 4 is your 2-bit adder lab. And there are very specific requirements for what you need to do for your lab report that you're not going to probably get from just reading through the description of the lab. So you really got to pay attention to this and ask questions if it doesn't make sense. All right, so experiment 1, you're playing with your 7-segment display. So these are these little sort of gray chips. They have 7 discolored regions on top. Each of those is an LED. You can run current through those and cause them to light up. So that's a picture of what the front of the chip looks like. This is what it looks like internally. So power gets connected to both pins 3 and 14 through a 1K resistor. And then if any of these pins, 1, 13, 10, etc., get tied to ground, what happens, you have current coming from VCC through your resistor, through the corresponding LED into ground, that LED will light up. So you always take 3 and 14, connect them through a 1K resistor to power. And then, depending on which, if any of these pins you connect to ground, different LEDs will illuminate. Okay, so there's note. It's important to add a 1K resistor between pins 3, 14, and VCC. Okay, so for this experiment, first step is a calculation. What's the maximum combined forward current through all 8 diodes? This is a little bit ambiguous, and there's a typo down here. This should say 3, not 13. So 3 and 14 are connected to VCC. Assume the LEDs have 0 resistance, and Ohm's law is V equals IR. So what's the maximum combined forward current? Well, there's 2 ways to interpret this, and you can talk about both of them in your report. One question is, if you turn on all 8 LEDs, how much current is going through each LED? The other way to interpret this is, what's the, under some condition, right, what's the most current you might have going through any one LED? Whatever that condition might be, right? So what condition causes an LED to get the most current going through it, and what is that most current? And this is a rehash of current parallel and series circuits. It's a thought exercise, right? So for part 1, there's nothing to build. It's really just kind of thinking about different configurations of this circuit. If nothing's connected to ground, there's no current going through anything. If I connect one of these to ground, say pin 1, then all my current's going through LED A. How much current is that? If I connect them all to ground, I have current going through all 8 of those LEDs. How much current is going through each? Okay, so play around with that analysis and write about it in part 1. Part 2, you want to make a circuit that lights up A, B, C, E, F, and G, everything except D, so it's going to look like the letter A. Right, so you want all the LEDs to be on except for D. So sketch a circuit that would cause that to happen, and then go ahead and actually build that circuit. And when you power it up, your display should look like a little letter A. And you don't need to get a signature for that, but it should be pretty clear to you if it's doing the right thing or not. If everything lights up or nothing lights up, your circuit needs some tweaking. Okay, so that's a warm-up. Main experiment is the 2-bit adder. So the goal here is to have 2 bits representing the number A, 2 bits represent B, and your output is a 7-segment display that shows the sum of those 2 numbers. So if you set your switches to say 2 and 3, the display should show a little 5. And if you set it to 1 and 1, then your display should show a 2, and so on. Okay, so let's make a list for experiment 2. So clearly identified independent variables and dependent variables for the 2-bit binary adder system. So system diagram. And explain the inputs and outputs. So how many inputs are going to go into this system? 4 inputs. And your inputs are going to be, and I recommend using this convention, A1, A0, B1, and B0. Those are 2-bit numbers. This should be the least significant bit. This should be the most significant bit. So how many bits of output do we produce? Well, what's the output doing? It's adding, right? So what's the largest number we can put in for this first number A? What's the largest value we can put in? 3. Largest value for B is 3. So what's the largest sum we can possibly get? 6. So how many bits do we need to represent a 6? 3 bits. So let's call those sum bit 2, sum bit 1, sum bit 0. So your system diagram should have 4 arrows going in, 3 arrows coming out. Label them something like this and describe what's happening, right? A1, A0 is a 2-bit number. This is the most significant bit, least significant. S210 is the sum of those 2 2-bit numbers. This is the most significant. This is the least significant. You got to have all that information there. If I just say it takes A, B, and adds them, there's no way I can take that and hook it up correctly, right? Ultimately, you're creating a unit that has 4 wires going in and 3 wires coming out. You got to know what those wires mean. So this wire is labeled A1. Well, what is A1? Is it the most significant bit of the first number? Is it the least significant bit of the second number? Right, so you got to spell that out. So explain the inputs and outputs of your system diagram. Okay, truth table for the system based on the input-output defined in part A. So this is a full truth table. Four inputs, 3 outputs, the same names you use in your system diagram. Okay, here's where it gets tricky. Minimized output functions in either product of sums or sums of product using a K-map. You want 3 equations here. S2 equals, S1 equals, S0 equals. As a function of your inputs, B1, B0, A1, A0, or their complements, right? Sum of product or product of sums, up to you. Nothing to do with full adders, half adders up to this point. Okay? If you even mention the word full adder, half adder up to here, you can take off a bunch of points. Because there's nothing in here yet that has anything to do with full adders or half adders, right? You can mention it, but don't jump to equations where S2 equals, you know, the output of some full adder that's wired together with a half adder and this kind of stuff. Start with the truth table and just write equations. Forget that it's doing addition. Okay, the goal here is, here's a truth table, here's the equations. And they're going to be ugly. They're going to be big and long. Okay? And then step D says, using the results from part C or your research into possible designs. This is where you can start talking about half adders, full adders. Because if you take the equations from your truth table and you try to implement those, it's going to be a lot of wires, a lot of chips. And we don't want to do that, okay, unless you really want to. But at this point, you can talk about, we can also do 2-bit addition by using a half adder, full adder design. Okay, and you can now spell out how you're going to do that. So show a picture of a half adder, write a truth table for it, write the equations for it. Describe a full adder, write the truth table for it, write the equations for it. Do your K-maps, all that kind of stuff. So at this point, discuss full adder, half adder design. Write truth table, minimize equations, and then circuits. And most likely the circuit you want to come up with in the end is using a half adder, full adder design. And I skipped something in part C. Clearly state the literal count and corresponding number of gates to implement each of the minimized output functions. So minimized equations, discuss literal count. That's how many terms you're ORing together if it's a sum of products, or multiplying together if it's a product of sums, plus how many gates are required. So write your equations, discuss the literal count, talk about how many gates are required to implement that. So that's the end of part C. All right, so part D, talk about half adder, full adder. Work your way to a schematic to implement 2-bit adder. And that's got to have your pin numbers and part numbers and all that stuff, right? Because that's the circuit you're going to actually implement. And so we want to include switches for input and LEDs for output. And you want an LED for each of these sum bits. And if you implement that and you put in 1, 1 and 1, 0 for your inputs, your output should be 1, 0, 1, 5. So these two LEDs would be on, this LED would be off, for example. All right, we haven't used the 7-segment display yet. So after you've got all of this going, after you can put in two 2-bit numbers and produce a 3-bit sum on your LEDs, now connect the 7-segment display. And that's a whole nother task. But this is where you want to use the 74LS47. So under supplies, there's a not very subtle hint here, which is use whatever 74LS chips are required. Consider using 74LS47. Definitely use that. Okay? That's what's going to let you take this 3-bit output and turn it into the 7 segments for your display. And the way you do that, we talked about this a little last week. So the 47 is this package up here. Basically, you got 4 inputs, A, B, C, D, and you got 7 outputs, A through G. And those 7 outputs correspond to the 7 segments, and based on the inputs A, B, C, D, it will display one of these numbers, or one of these symbols if your number is bigger than 9. So which LEDs do you light up in order to display a particular 3-bit number? You don't have to worry about it. That's what this chip will do for you. So if you want to display the number 0, A, B, C, D should all be 0. If you want to display the number 1, D, C, B should be 0, A should be a 1. If you want to display a 2, D and C should be 0, B should be 1, A should be 0. Our highest possible sum is a 6, so it's only these first 7 rows we need to worry about. And in all of those rows, it looks like D should be a 0. So connect D to ground. And it looks like C, B, and A should just be the binary version of the number you want to display. So S2 goes to C, S1 goes to B, S0 goes to A. So D to ground, your S outputs from your previous circuit go to C, B, and A. LT bar should be high. RBI shouldn't matter. Actually, RBI should be low. And I think that's all you need on the chip. And then hook up these to the 7 segments of your display. On your 7-segment display, connect 3 and 14 to power through a 1K resistor. Fire it up and you should get nice numbers being displayed. But you're doing it in steps, right? So all of this is designed. When you start building, first just drive 3 LEDs. That'll tell you if you're adding correctly. Once your adder is doing the right thing, now go ahead and hook in the 7447. Otherwise, you're getting the wrong thing on the 7-segment display. You have no idea where to debug. Right? So get the adder working first. All right, I'm going to put one more requirement on this. So here's your proto board. Wherever you put your switch block, okay, I don't care where it is on the board, but wherever you put your switch block, I'd like you to wire your switches like this. I want this rightmost switch to represent A0, the switch next to it to represent A1. I want the leftmost switch to represent B1, and the switch next to that to represent B0. And then the 4 switches in the middle don't do anything. And if you're demonstrating your circuit to me, I'm going to insist that that's how it works. So if I want to do 2 plus 3, for a 3, I would turn both of these switches to whatever position represents a 1, and I'd turn this to be a 1 and a 0. And on your LEDs, somewhere in your proto board, you're going to have 3 LEDs. Wherever you put those, put the most significant bit on the left, and then the next bit, and the least significant bit on the right. And it sounds like a trivial OCD kind of thing, but I have watched so many students trying to debug a circuit that's either already working or is failing in some different way because the way that their wires ended up running, they had S1 and then S2 and then S0. and now they're trying to add 2 and 3, and they're hoping to get a 5. And so a 5 should be, well, that should go there, and that should be a 1, and that should be, right? And there's so many opportunities to get confused, and it's already a complex enough lab as is. Make life easier on yourself, right? Keep your switches in a well-defined order, keep your LEDs in a well-defined order, so that you're not chasing ghosts. Because I find students all the time doing this, and when we get down to it, their circuit's working perfectly, but they spent 2 hours trying to figure out what's wrong because they were interpreting the switches wrong or interpreting the LEDs wrong, right? So do it like this, right? Most significant bit to least significant, most to least, left to right. And keep B over here and A over here. Don't intertwine A0, B0, A1, B1, right? Separate them out. It will make it easier to test. All right, and then build your circuit, demonstrate it to somebody, get a signature showing that it worked, you're good to go. Lessons learned, new experiment at the end as usual. So this is where all the work is, right? Experiment 1 is kind of a warm-up. Experiment 2, half of this is just done on paper. Nothing that you have to do with circuitry or test equipment. And the biggest thing is, don't get into the full adder, half adder stuff until you get down to here. Just do a straight truth table for a 2-bit adder. We did this in class, right? And write equations from here just like you write equations from any truth table, right? Completely ignore full adder, half adder. Minimize those, how many gates are required, how many terms do you have added together, and then say, well, I don't want to build that, I'm going to use a full adder, half adder design. Now you got to do some more work, right? Block diagram for a full adder, truth table, equations, minimize them. Same thing for a half adder. Now show how the full adder, half adder get connected together, go into the switches, part numbers, pin numbers are good to go.
How do we actually draw the 74LS32 and the LED in our circuit diagram?
The 7-segment display, you mean?
Yeah, that.
So 7-segment display, you could do it just like this. And just show your inputs to it like that. And just label it in your component ID block as 7-segment display. And that's easier than trying to like draw the wires over to the segments, but anything that makes it clear there will be good. All right, so let's do a week from today. All right, you're good for a break. Come back 5 minutes. And we will start something new.